This paper describes how to search for a target for an unmanned aerial vehicle using adaptive submodularity and deep learning. The authors are Yu-Chung Tsai, Bing-Xian and Kuo-Shih from Robotics Search Lab of the Mathematics Department at the National Central University. The purposes of this project are as follows. The main objective is to enable an unmanned aerial vehicle to adaptively search for a person in a non-3D environment. Deep neural network is to learn the target distribution. Adaptive submodularity is to compute the maximum coverage. The experimental environment is 5 meters by 5 meters square in a classroom. The robot platform is an Intel ready-to-fly drone. There are 3 major sensors. There are 200 cameras is to sensor the environment. The Intel neural stick is to detect the target. The PS4 flow is to estimate the drone's position. All of the computations are executed on the drone, except to the target detection, greedy algorithm and DNN. The drone and neural stick exchange image data and detection outcome via the USB interface. The other data are exchanged via ROS. A cloud server with a GPU computation executes the training and prediction steps of DNN and sends PO5 to the drone. The experimental parameters are shown in this table. The flowchart simply describes the process of the experiment. The drone takes off and moves to the first sub-goal. Once the drone arrives at the sub-goal, it will hover to detect the target for 3 seconds. During hovering, the drone tries to detect the target. If the target is not found, the drone will move to the next sub-goal. Once the drone is found, or cannot find the target after arriving at the K sub-goals, the search is terminated, and the drone will land on the ground. After landing, we take the search result to update the neural network. There are 6 layers in the neural network. The first layer receives an image. The second and the third layers are 2 convolution layers, followed by 2 pooling layers. The fourth and fifth layer are flattened and hidden layers. The sixth layer includes 2 neurons with softmax function to represent P of phi I equals to 1 and P of phi I equals to minus 1. There is the experiment video. The green rectangles and decimal numbers represent the detect area and corresponding probability respectively. We use the detect result to update by best filter. The figures show the search paths of submodularity and adaptive submodularity approaches. The red circles and blue cross marks represent the drone takeoff point and detection point respectively. The gradient color lines between red and blue represent the search paths between taking off and landing points. The experimental results are summarized in the table. The expected time to detection of the proposed algorithm is 22% faster than that of the benchmark algorithm. The successful rate of the proposed algorithm is 10% more than that of the benchmark algorithm. These experiments demonstrate that the proposed algorithm outperforms the benchmark algorithm.